Today I'm going to talk about a paper that was published recently, came out of the Blyth Institute and is published in the journal Biocomplexity, and it's called Measuring Active Information in Biological Systems. And I think it covers some important points of evolutionary biology that are often missed. So here you can see the paper, and as I said, it's Measuring Active Information in Biological Systems. It's in the 2020 volume of Biocomplexity, and it's issue 2, pages 1 through 11. So the paper is about whether or not organisms direct their evolution, and more importantly, how would we know? Okay, so the problem is that it's widely believed by many both that directed mutations don't occur. And there's a lot of reasons for this. There was a lot of hoo-ha about directed mutations in the 80s and the early 90s that kind of fizzled and faded away. But overall, the reason why it's believed that they don't occur is because usually most investigators have a single specific idea of what a directed mutation will look like. And therefore, when you disprove that one specific idea, to everyone else, that serves as a disproof of the whole concept of directed mutation. So, but that's not really a fair way of measuring it, because there's a lot of different ways that something can be directed. And so, what we actually need is that we actually need to find a way to measure directedness that's independent of our specific ideas of what something should look like. So let me just pose for you just kind of a thought question. And there's not actually a right or wrong answer to this. I just want you to think about it. So let's say that we have an organism and it's undergoing selection. And there's a beneficial mutation that occurs in 0.01% of the mutational events. Is that directed? Okay, so think about that. So there's a beneficial mutation in 0.01% of the mutational events. Is it directed? Okay. So the questions you should ask is, should it be more, if we're going to classify it as directed, does that cover the bounds? Is it 1%? Is it 100%? Is it 10%? At what point are we calling it directed or not? Okay. But more important than that, how would you know? Right? That's the big question. How would you know? So that's what I aim to answer, because we could set an arbitrary cutoff point, but how would we know that was a good cutoff point? So anyway, so that's what I was thinking about when I was writing this paper, is how is there a way that we could measure this in a way that's not about what I think or you think, but a way that's actually objective, that we can objectively determine whether or not a mutation is directed. Okay, so what I figured out what we need is we actually need an expected value for the beneficial mutation rate. We need to know, well, what would we just expect if these mutations actually were random, and by random I just mean haphazard. If they're happening haphazardly, what is the mutation? What is the rate of beneficial mutations we would expect to get out of this organism? Okay, so then if we have that expected value, we can then judge whether or not an outcome needs explanation. So if we have an expected value for how often this organism should be producing beneficial mutations, and it's producing them about that rate, well, that doesn't need explanation, because we know what the beneficial rate would be expected to be, and so if it's about at that rate, well, that's what we expected. So it doesn't need an explanation. But on the other hand, let's say that we determined through whatever means, and we'll get into those means later, that we expect that 1% of the population to generate beneficial mutations, but actually 20% of the population generated beneficial mutations. Well, being that far away from expectation would demand some sort of an explanation. So that means that the organism itself, there's something in it that's directing mutations. Okay, so the benefits of doing this is, if we're able to measure whether or not a mutational event requires explanation, that allows us to focus research on systems where we have a justified reason for expecting a mechanism. Okay, so think about this. It costs a lot of money. People oftentimes forget that research costs a lot of money, and investigating whether or not and the mechanism for directed mutations actually costs a lot of money. And there have been investigations where they have found directed mutations and very well documented, but the problem is that all of these cases required a large number of experiments. And so if we just go about, for every beneficial mutation we see, investigating whether or not it had some sort of mechanism behind it, well, we'd spend a lot of money possibly going down wild goose chases. So if we know ahead of time which mutations are going beyond expectation, then that gives us a place that we can focus our research dollars on places where we actually expect to find something worthwhile. The other thing is that if we have a way to measure this, is that we can actually, not only can we characterize the characteristics of an organism, we can actually characterize the mutable range of an organism as a property of that organism type. And so this is called, by Caporal, she calls this the implicit genome. How far is the genome implicitly geared to be modified? And so it'd be great if we could measure that as an actual property of an organism. And then, this has obvious biotech benefits. If we know how something is likely to evolve, this can help us with waste cleanup and all sorts of things where we have something where we have, we know that there's this thing that we're trying to clean up. We know that there's this organism that can evolve in that direction. So we put them together and we can do biotech magic with it. And then for design, having a mechanism that yields adaptation triggers what's called Dembski's displacement theorem. And this is one of the most, I think, underrated theorems in all of intelligent design, but that's beyond the scope of what we're doing today. But if you have a chance, look it up. I'll try to do a talk on it at some other time because it's actually really fascinating. So now all of this is predicated on us finding an expected value. Okay, so how would we go about finding out what is the expected value for getting a beneficial mutation in a certain scenario? Okay, well, to start out with, we have to find a mathematical way of thinking about evolution. Okay, and so what we're going to do is we're going to view evolution as a search. And so now, whether or not you think evolution is a search, like philosophically is a search, mathematically, we can model evolution as a search. Okay, because when an organism's under selective pressure, evolution can be modeled as a search through genomic space to find a set of mutations that relieves the selected pressure. And so because we can model it as a search, the mathematics of search will hold whether or not evolution should be viewed ontologically as a search, whether or not it really is philosophically a search. Since it matches the mathematics, we can use the mathematics to tell us more about it. So now one thing that a lot of people misunderstand about this does not mean that it doesn't require that evolution is searching for a specific target. Search does not have that requirement. It just means that there's a criteria that we can determine to know when it found what it was looking for. So in this case, we can say that the goal is the set of all mutations which will cause it to relieve the selective pressure, right? So that is a search. We can define a search that way. And so then the mathematics of search will hold, okay? So now within search, there is a theorem called the no free lunch theorem, okay? Now, remember the hypothesis that we're testing is that evolution is a blind process, okay? Well, the mathematics of search show that on average, a blindly chosen search process is no better than a random walk, okay? And so this is called the no free lunch or NFL theorem. And this allows us to find an expected value for a mutational process, okay? Because on average, which would be the expected value, a blindly chosen search process is no better than a random walk, okay? So therefore, if we can make a random walk, then we can find an expected value. So to find an expected value for what a blind process will do, we should ourselves perform a random, that is a uniform random distribution, or our closest approximation to that, ourselves perform a random search for the answer. And then the rate of beneficial mutations that we find in our random search gives us the expected value for just an arbitrary, non-directed search process. Okay, so we're going to do a random search, and that's going to give us an expected value for an arbitrary search. Okay, so if the claim is that mutations are not directed, well, that's what an arbitrary search would be. It's something where the search is not directed toward the outcome, so it's arbitrary. And interestingly, what the no free lunch theorem says is that a random search will give us the expected value for an arbitrary search. Okay, so that's quite interesting. So now, again, I want to make sure I'm clear about this, because a lot of people misunderstand what I'm trying to say. This does not mean that I believe that mutations follow a uniform random distribution. I don't. In fact, the whole point of this is that I don't think that they're following a uniform random distribution. It also doesn't mean that I think evolutionary theory as it currently stands does as well. The point of a uniform random search is to establish an expected value for what an unguided search process will give you. Okay, it's establishing an expected value. So, all right, so to measure this, we're going to use a tool called active information. And the best place to go for about active information is the original paper, Dembski and Marks 2009. And it's their conservation of information and search in that IEEE journal listed there. So, active information is the comparison of the success rate of a particular algorithm to the success rate of a blind search process, which is what we're doing. We measure active information in bits, and bits, if you have a probability, you can convert back and forth between probability and bits, because bits are the negative log 2 of the probability. And so that's basic information theory. I'm not going to go into that here. So high active information means the algorithm is directed towards the goal. Low or negative active information means the algorithm is not directed toward the goal. Okay, so active information can be negative, and so if it's negative active information, it means your search process is actually worse than a random search. Because remember, the random search actually gives you average expectation. Okay, so it could be more than that, and it could be less than that. Okay, and so we're going to come up with a number that's in bits. And one thing to keep in mind about bits is that the number of bits of active information is actually an order of magnitude measurement of deviation from the expected outcome. Okay, so if I say it's 4 bits, that's 4 orders of base 2 magnitude. Or if you prefer base 10 magnitude, you can multiply the result by about 0.3, and that'll give you how many orders of magnitude using base 10 magnitude, however you feel comfortable measuring things. So, and we use order of magnitude measurements because the actual probabilities get kind of crazy if you don't do that. So the way to visualize active information, just if you're having trouble figuring out what this is. So let's say that the gray area represents the full possibility space, and the little blue dots represent targets. Okay, and so hitting any of the targets, perfectly fine. That's a success, is if you hit any of the targets. And then the green area is the space that we're actually going to search. Those are going to be the places where we actually look for solutions. Okay, so if you are looking in the wrong place, that's the the thing on the far left. If you're looking in the wrong place, you have negative active information because the targets are there, but you're not looking there. Okay. If there's just a partial overlap where it's it's about as if you notice targets make up about a quarter of the are found in about a quarter of the possibility space, and that restricted space in the next one over, there's targets in about a quarter of the possibility on the restricted possibility space. We have pretty much zero active information. It's low zero, just in that area. If our restricted search space lines up largely with the targets, that's moderate active information, and if we're right on the targets, that's high active information. Okay. Now, a few notes. First of all, this is entirely for visualization. First of all, the search doesn't have to restrict you physically to a space. There's all sorts of different ways that you might be searching this space, not just in a box in a 2D grid. So that's just to help you visualize what's going on. So they can be simple, they can be complicated. There's all sorts of ways to narrow in on where you think the targets are going to be. The other thing is to recognize this is just a visualization. If this was real life, the actual amount of information gained, even by the one that's in high active information, would be very small because you already have you're only restricting the space a little bit. So even with the one that says high active information, it actually would be low if you're taking this graph literally. Okay, so I just want to be clear. This is meant to visualize it, not to be an actual graph of something. So a little bit of terminology. So you have endogenous information. This is the probability in bits of finding a target by a random process. Now notice that this has a different meaning than it does in biology, because remember this came from search, came from a journal in the IEEE, and so when they talk about endogenous information, they're not. In biology, endogenous information means information that we find in the genome, and that's not what it means in active information. So in active information, you might see the word endogenous information. That is the probability of finding a target by a random process. Okay. Exogenous information is the probability of finding a target by a particular search process. Okay. So the one that's by a particular search process is I_S, and the one at random is I subscript S and I subscript omega. So active information is I subscript plus, and that's the difference between those. It's just it's I omega minus IS. Okay, so that's how it is determined. Now, just to note, active information is actually always relative. There's always some sort of a background that we're considering. So this is in engineering, we have other concepts like this. So if you think about decibels, decibels are always relative. But we usually have, oftentimes we talk about sound in terms of decibels, where we don't state what it's relative to. And so in that case, we're usually talking about a specific reference that we're comparing to. And so with active information, our general reference is the whole genome. Okay, so we'll later cover how to use this in a more relative sense, but in the general case, we'll be using active information relative to the whole genome. So what I thought about is that, okay, so we have these ideas. These ideas, they didn't originate with me. As I said, Dembski and Marks wrote about them in 2009, and there's been further work on it since. And mostly, though, they've been dealing with digital search and digital evolution and that sort of thing. And so I want to know, how could we apply this to biology? Okay, so how could we make this so that we can experiment and find quantitative results? So so my goal is to get people thinking about how to apply active information to experiments. various difficulties an experimenter might encounter, and how you might overcome those mathematically. Okay, so my goal is to come up with a system that would kind of take these things into account. Now, of course, depending on your own requirements, the system may have to be tweaked or whatever to work exactly for your situation. But my goal is just kind of get people started, get people thinking about it, and just kind of think about what are, not only what are we trying to do, but what are the problems that could get in the way, and how might we overcome them. So let's start by applying what these terms would be in biology. Okay, so given a selective pressure, we can easily measure the probability of an organism finding a solution. Okay, so we just figure out how many organisms there are, how many of them found the solution. Okay, so you convert that to bits. That is I_s. Okay, so the question is finding a solution by chance easier, harder, or the same? Okay, so we know how hard we know what the probability is for the organism itself to find it, but the question we're asking is the organism, is this a haphazard process, or is this a directed process? And the way that we do that is we figure out, well, what's the probability of it encountering this by chance? And so to figure that out, we have to experiment to find out whether or not actually random mutations are more or less likely to find the target. And so the ability to find a target by random chance will be I-omega. Okay. Now, interestingly, there's actually quite several important difficulties in finding I-omega. So biology itself presents several problems for finding I-omega. The first problem is that it's hard to guarantee that the mutations we induce are random. So in kind of a low-tech way, one solution would be to use a variety of broad spectrum mutagens, and we use basically the coverage principle to say, well, these may or may not be exactly random, but we're covering a pretty widespread selection of spaces to kind of simulate randomness. A better solution, if you have the technology to do it, is to use direct gene editing with a large library of random edits. Okay, and so this is a technology that's come about in the last few years. And so if you have the ability to do that, that's an even better way of finding I-omega. But another problem is that it's basically impossible to turn off the cell's mutation system without impacting the cell in other ways. Okay, so the cell is always going to be generating mutations. So you're going to be asking yourself, well, when I tried to introduce random mutations, were the mutations that were generated actually random, or were they generated by my process, or were they generated by the cell's process, or a combination of those? It's hard to know. So the solution to that is statistical trickery, which we'll talk about in a little bit. And then the final problem is that the target, there's actually some targets where cells are hitting them, but they're actually too small to hit by random chance. And if you have 0 hits experimentally, that's the same as having an infinite I-omega. Okay, but it's not actually infinite. It's just the number of hits are too small to be measured. Okay, so that makes actually measuring the information impossible. So the solution is to create a minimum practical bound for I-omega based on the smallest known successful mutation and the mutation rate. And we'll talk about that later. That's kind of a side issue, just kind of how do you solve this problem where you're literally getting 0 hits for random mutation because the target's just too hard to find. Okay, so now I want to give you a conceptual model for what we're going to do. So imagine 2 plates of bacteria that we're testing, and we're testing them against a selection pressure. And on plate 1, we're only testing how the organism itself succeeds. Okay, and so the kind of gray stars are cells that didn't mutate at all, and the green stars are cells that did have a mutation. Now this diagram doesn't talk about whether they're successful or not. It just, these are ones that have the mutations. Okay, On the second plate, you're going to be inducing mutations. But as I mentioned, the cells themselves are also generating mutations. So both things are going to be happening. So you can see there that you have some mutations that were induced, okay, or that were internal to the organism. Those are still your green ones, the ones that the organism itself does. The red ones are going to be the induced ones by your random edit library, or however you wanted to induce random mutations. But there's going to be some organisms that are hit by both, and so that's indicated by the gold star. That's an organism that was hit with both internal mutations and induced mutations. So both of those happened. Okay, so that's kind of what we're dealing with. We're going to have two plates. One of them we're going to measure the mutation and success rate for internal mutations. The other one, we're going to have all these things happening. We're going to have internal mutations, induced mutations, and then combinations of those. Okay. So the big problem is figuring out the effect of these shared mutations, the mutations that are hit by both our induced process and the cell's internal process. So we can, if we figure out how many could be affected by that, we can find a minimum and maximum I omega based on either fully including them or fully excluding them from the success rate. Okay, and once we have that, we can use these to calculate a minimum and maximum active information. So the calculation is kind of ugly, but it looks like this for the maximum. It looks like this for the minimum. And so what these mean is that so NC1 is the number of organisms under study in plate 1. NC2 is the number of organisms under study in plate 2. Then UC1 is the internal only successes. UC2 are the total combined successes for plate 2. Then the OS is the per organism mutation rate from internally generated mutations, and O omega is the per organism mutation rate for externally generated mutations, the ones that we induce. Okay, and so that's what those things mean. And so you can read in the paper more how that's derived. But the important part is this little guy is kind of our little error amount. This represents the mutations that get hit in both the internal mutations and the external and the induced mutations. And so you'll notice that one of the that Imax, active information max, fully subtracts those, and minimum doesn't. So somewhere in there is the active information. So anyway, so that's kind of the math that you can use to kind of get out of the problem of having to keep the internal mutation mechanism of the cell around while you're trying to mutate as well. So now I mentioned the problem where what happens if you don't have any hits on randomly generated mutations. How do you measure the active information there? Okay, so we can use the minimum mutation size to figure out at least an estimate for what that should be. So I'm calling this the configurational complexity. It's the chance of hitting. So basically, you find what's the smallest successful mutation we found. Okay, and we'll just kind of have that as the stand-in for what is the required number of mutations. So we'll find the smallest one, and then the probability of hitting that is kind of this ugly guy, and then this is how you calculate active information from it. So in this, the genome size is G, the length of the small successful mutation is L, and the per base pair mutation rate is M sub S. And so for more on how that's derived, you can see the paper, but that's how you can calculate it. Now, I want to show some example outcomes so you can kind of get a feel for how this works. These are not actual experiments. This is just, I'm just trying to show, if you receive this kind of result, this is what that would mean. Okay, just to give, just to kind of help you recognize what the different pieces are. So, the first example will be moderate active information. So this organism under this selective pressure exhibits active information. Here's what would be something that would lead to that. So we're going to have 10 to the 9th organisms. We're going to have an internal per base pair mutation rate of 10 to the negative 10th. Okay. And then the external per base pair mutation rate is 10 to the negative 9th. And one thing that's important about this, I forgot to mention earlier, is that for this to work well, the mutation rate actually has to be significantly smaller than the genome size. So it needs to happen so that it's more likely to not receive a mutation than to receive one. Okay. Otherwise, the overlap between internally generated and externally generated mutations cause it to be swing too hard both ways. So let's say that so we got 10 to the 9th organisms. So let's say that we have 10,000 successes on internal only, and on our combination we have 10,005. Okay. So you can see that our external mutations are only contributing a small number of added successes. Okay, so that means that this was actually a moderately hard target to hit. As I said, random mutations are only giving us a handful of solutions, but the random mutations are only giving a handful of solutions above and beyond what we were getting at random. Okay. And so this guy gives us a range of 13.4 to 16.6 bits of active information. Okay, so our internal processes are much better than our external processes, but there's still a chance of hitting the solution with external processes. So it's moderate active information. Okay. So here's an example of negative active information. So as I said, you can indeed it's in theory possible to have to score negative on active information. That means that the organism's search process is worse than a random search. Okay, so here basically the same setups. So the number of successes that we're going to get with our internal mutations is 10. Okay, so we only got 10 successes that were internally generated. But when we added in our random mutations, which were occurring at about the same rate, we got 1,100. Okay, so that means that there were a lot of mutations that were findable that the organism wasn't finding. So its own however it finds mutations, whatever mechanism is going on that's mutating, is not aligned with what would generate a beneficial mutation. So in this particular case, we have negative 6.82 to negative 6.71 bits of active information. So that means the internal process is actually pointing away from potential positive results. Okay, so here's an example where the mutation rate is too high to evaluate. So our internal per base pair mutation rate is 10 to the negative 6th. Our external per base pair mutation rate is also 10 to the negative 6th, but we have a very large, we have a 10 million base pair genome, so it's going to be large enough that it's not going to bode well for our calculations, and we're going to wind up, so with internal only successes, we have 10,000. With combination successes, we have 10,100, but there's so many overlaps that the amount of active information is anywhere between negative 16.61 and positive 62.37. So anyway, it's basically a range that's too wide to tell us anything useful at all. So here's one that shows you the usefulness of Pconfig. Okay, so we're going to have an internal per base pair mutation rate of 10 to the negative 10th. Same for external. On plate 1, we're going to get 3,000 successes. In plate 2, we're also going to get 3,000 successes. So it's not apparent that the external process had any successes. So on the large end, it's, if you actually subtract it off, it could be that the random processes had zero effect, that it found zero of them. Okay, well, that would be infinity. That would give you an active information of infinity if it was literally not findable. But everything is at least in principle findable, and so we can use the Pconfig equation to figure out what is the in theory probability of finding the smallest mutation. And so that's what we're going to use to do our upper bound in this case. The lower bound we can find, but the upper bound is hard to find. So it's between 12.9 and 86.1 bits of active information. So it's definitely a directed mutation, but how much we don't know. So this next example is an insertion sequence. And this actually comes from, it's not exactly replicated, but there was an experiment by Barry Hall, and I don't know all the parameters for it. So I tried to get this one to be at least roughly commensurate with kind of what he found. He basically found that there was a large insertion sequence that was that an organism could generate in response to certain stresses. And so it was about 12 base pairs. This did not get generated at all by random chance. So anyway, in that case, it would you could only go by how many base pairs the smallest mutation was, which in this case was 12, and so that would be 361.2 bits of active information. So anyway, I'm not directly saying that about that particular experiment. I'm just saying this is the kind of thing that we can be looking at, that we can go back to some of these experiments and actually provide measurements for how much information is this organism contributing to its own evolution. So that's kind of a general case model. Even being general case, it's got some restrictions on it that actually you can only really use it in organisms that have pretty small genomes. But there's also some simplified models we can use as well. So the first one we're going to look at is restricting search space. So an example of this is somatic hypermutation. And this is the process that the immune system uses to generate new antibody genes in response to newly identified invaders. Okay? And the way that somatic hypermutation works is by restricting mutational search space. Okay? It basically limits the mutations to pretty much only occur on the correct half of the correct gene, and we already know that this is the biologically correct gene to be operating on because it's the antibody gene. Okay, it's not doing this on other genes. It's basically saying, okay, well, I've got this antibody gene, and how can I modify it? And it's literally focusing mutations on the correct half of the correct gene, that biologically we know this is the right gene to use. So since we already know that the search space restriction is biologically meaningful, this means we can assume that the reduction in space is entirely active information. So we know that the mutation needs to occur here. And so as a simplifying assumption, we can just take that reduction in search space entirely as active information because we know it from biology that this is an appropriate reduction in search space. And it is somewhat of a simplifying assumption because there could be somewhere a mutation that would also solve it that's something else, but I think by and large this is a worthwhile simplifying assumption. So the way we do the math for restricted search spaces is that if G is your genome size, Z is the reduced mutation space, and M is the number of required positions needed for successful mutation, you can calculate it like this. Although that's It's kind of messy because lots of factorials with lots of big numbers. A lot of things don't like to calculate it. So you can simplify it, and it's a simplified approximation. You can see how we got it in the paper, and you can see that, you know, for this calculation, for the somatic hypermutation system, active information gives you about 61.5 bits of information. So now this was calculated using the simplified one, but I also calculated it using Wolfram Alpha, and I was within 0.0022 bits of using the more complicated formula. So it actually, for if you have a large G and a small m, it works out pretty well. So anyway, so what does that 61.5 bits mean? It means that the organism search is more than 60 orders of magnitude away from the expectation. So that means that's pretty sizable. So that's restricted search spaces. So the next one we're going to look at is relative active information. And so this is something that you can do if you have, I kind of did it for looking back on other people's experiments where they're not always following what I would have wanted them to do, but nonetheless gives me a good estimation of it gives a good place to apply active information even when not all of the experimental controls I might want are in place. So for example, you have Linsky's long-term evolution experiments. So they detected a mutation of E. coli, which allowed the use of citrate as a carbon source under oxic conditions. Okay, and if you look at their various experimental parameters, you can actually it looks like it occurs about once out of every 10 to the 10th mutations. Okay, but there was another experiment where Hofwegen, so the long-term evolution experiment, these organisms were not under selection. But Hofwegen did a similar experiment under selection, and if you examine their experimental parameters, it looked like it occurred once out of every 1.8 times 10 to the 6 mutations. So what you can say is you can talk about active information relative to selection. So both of these are the organism's own internal search space, but one of them is when it was being guided by selection. So the organism is detecting the selection and generating a response in response to the selection. And so you can measure that with active information. And so the active information relative to the non-selective rate is about 12.4 bits. So in other words, under selection, which corresponds to the organism's need, where this outcome actually becomes a target, the mutation appeared 12.4 orders of magnitude more often than when it wasn't needed. Okay, so the organism is directing its mutation process based on its need. So, in summary, the question of whether mutations are directed can be determined if we have an expected value for the beneficial mutation rate. The no-free lunch theorem allows us to find that expected value by analyzing the effects of truly random mutations. And then active information gives us a measurement of the deviation from that expected value. The active information will tell us if the mutation system is pointed toward, away from, or neutral to the solution set compared to a random search. Active information is great because it's agnostic as to the mechanism of direction. It doesn't care what directedness looks like. It doesn't say, well, it needs to follow this mechanism or that mechanism. It just says, well, I'm just going to detect if the directedness is there. How the directedness is implemented, we can find out later. I'm just here to tell you that there is or there is not directedness towards the result. So this allows biologists to figure out where they should be pointing their research, because we can figure out that there's directedness before we figure out how there's directedness. So this provides lots of benefits. As I mentioned earlier, if you find a mutation that has positive active information, this provides justification for additional research into mechanisms. Having a catalog of organisms and what sorts of contingencies that they contain, that they contain active information for, can assist for a variety of biotechnology tasks. And a directed mutation system can provide the evidence for the first stage of invoking Dembski's displacement theorem, and this will count as evidence of design in organisms. So as you can see, active information can fill a lot of interesting roles, and it can help us to look at the biology of mutations in a totally new way. So anyway, I'm excited for the future of active information, especially as applied to biology, and I hope you are too.